Okay, who's ever heard of the slogan "Cogito ergo sum"? Nobody. Okay, all right. How about "I think, therefore I am"? Anyone ever heard that? A couple of you. It was part of the basis of the philosophy for Rene Descartes, and I mention him here because he's the one that first came up with polar coordinates. Now, at least that's what I read once. I always thought it was Euler. In any case, polar coordinates are a different way to think of defining a point. Instead of x and y, meaning the distance along the x-axis and the distance along the y-axis, you can think of r and theta. That is a radial distance and an angle above the x-axis. So it's a different way to specify a point. Let's see if we can't come up with a few relationships amongst x and y to try and understand polar coordinates. And then eventually our goal is to graph functions in polar coordinates, find their derivatives in polar coordinates, and then find the areas of functions defined in polar coordinates. So a lot of work in front of us. We'll split it up in a couple sections. But we'll start with a very simple one. If this is x and this is y, then one relationship we can get real quickly is x squared plus y squared equals r squared. And of course from that you can also get r as the square root of x squared plus y squared. What else can we get? Well, if this is theta, then I can get cosine of theta is what over what? X over r. Or following from that, r cosine of theta is equal to x. So those two things are interchangeable. Cosine, there we go. Likewise, what's the sine of theta going to equal? Y over r. And from that, r sine of theta is equal to y. So a couple nice relationships there. There's one last one that I want to get, and that is the tangent of theta. Tangent of theta is not going to involve r at all. It's just going to be y over x. And from that, you can get theta equals the inverse tangent of y over x. So, okay, so a couple quick relationships amongst your variables here. These are some reminders on how to derive those things. When we're graphing things in polar coordinates, we're always going to graph things in the form of r and then theta. So let's practice plotting a few points that are in that form. We'll start with problem number 2. We'll do 2 and then 6, and then do a couple more examples. So problem 2, you know what, let's tell you what, let's do a couple versions of problem number 2. First we'll start out with 2 and then 5 pi over 3. And then we'll go do the problem that's actually in the book, negative 2 and 5 pi over 3. Likewise with problem number 6, we'll start out with 2 and 11 pi over 6. And then we'll do negative 2 and 11 pi over 6. And then we'll do a couple more here. 4 and negative 3 pi over 4. Along with negative 5 and negative 4 pi over 3. So a lot of examples here to work on, and I gave you a little corner here that we can plot some of these things. It's a little bit more friendly to plot on than your regular x and y coordinates. We'll start out with problem number 2, kind of a altered version of that. We want to find the point 2 for your radius and 5/3 pi. So let's start by finding the angle. 5/3 pi is down here. So it's along this line, and we want to move a radial distance away of 2. So 1 and 2. So that would be your first point. Let's try problem number 6-ish, which was also at the point 2. This time we are at 11 pi over 6, so we're trying to graph this one, 2 and 11 pi over 6. So find the angle, move a distance of 2, 1 and 2. But if you're looking carefully at the problems in the book actually have a negative radius, so -2 and 11 pi over 6. That was the actual problem number 6. To account for a negative radius, instead of moving out in the direction of your angle here, you're going to move 180 degrees in the opposite direction. So the actual point here for problem number 6 would be along this line right here, 1 and 2. So that's problem number 6. Likewise, for problem number 2, instead of moving a distance of +2, we have to move a distance of -2. So move 180 degrees opposite of that. That's going to be up here for problem number 2. Now I suggested a couple more. Suggested, say, 4 and -3/4 pi. When you're moving a negative angle, all that means is that instead of rotating counterclockwise, you're going to move clockwise to find your angle. So -3 pi over 4 is going to put us over here at a 225 degree angle, or 5 pi over 4, and then a radial distance of 4. So 1, 2, 3, 4. Right there. The last one was kind of a double whammy. -5 and -4 pi over 3. So you got to account for a couple things here. You've got to account for a negative angle and a negative radius. Start with the angle, then find that angle, find your point, and then take account of the negative radius. So that one there. Boy, he's loud. He's like 2 rooms away, I think. All right. What quadrant does this land in? Second, third. All right. Well, let's find out. So -4 pi over 3 is kind of like a negative, negative 240 degrees. So that'd be over here in this quadrant. A distance of 5, 1, 2, 3, 4, 5. So we're out here. And then we need to move opposite that. Actually, I should have moved along this line. 1, 2, 3, 4, 5. Then move opposite that by 180 degrees. So I think it ends up here. Let me just double check that. -4 pi over 3. That's equivalent to a negative 240 degree angle. So that'd be a negative 240 degrees. Would put you here at 120 degrees. Point to 5 would be here, but we've got -5. So I'm thinking it should be right here for that point. Okay. Now, we're going to play a little bit with converting back and forth between rectangular coordinates and polar coordinates. These relationships are going to help us. If you don't memorize them, that's fine. Just make sure that you can do what we did, and that is derive them for ourselves. For starters, we're going to, let's see. Let's convert a few points to polar coordinates from rectangular coordinates. So convert to polar coordinates. We'll start with the point in problem number 12, 0, -6. Might not be a bad idea to graph this and see where it's at. Where's the point 0, -6 going to be? Yeah, it's going to be down on the y-axis. So down here. And I think we can do this one by inspection. So right here, we need to know 2 things. We need to know the angle and the radial distance. right here. So see if we can figure out both of them without necessarily resorting to any special formulas or something like that. Let's start out with theta. What angle is it to go from the positive x-axis down to the y-axis? 270, or better yet, since we're working in calculus, this would be in radians. 3 pi over 2. Good. And how about the radial distance? 6. Good. Not negative 6, positive 6. So equivalently, this point would be 6 and 3 pi over 2. Yeah, that'd be an equivalent way. So that's something that's kind of interesting about polar coordinates, is that there's a lot of different names for this point. So the one that you just mentioned would be negative 6 and pi over 2. That would work because pi over 2 would put you here. Negative 6 would bring you down here. So yeah. How about 6 and, let's see, what would it be? 5 pi over 2? No, it'd be 7 pi over 2, right? Yeah, 7 pi over 2. And so on. You can just add multiples of 2 pi to that and keep on generating more and more equivalent points. So yeah, nice observation. Let's try problem number 14. So we got the point 4 and negative 2. Let me first graph that. All right, so 4 and negative 2 is going to be here. We're going to need two things. We're going to need the radius and the angle. So I want this angle here. That's going to be theta. Theta is always measured from the positive x-axis, going counterclockwise around to your terminal ray. And then I also want to know what r is. How far out is this point? Let's start out with this. Start out with r because it's going to be easiest, I think, to get r. Remember, r squared is x squared plus y squared, so r is the square root of x squared plus y squared, or the square root of 4 squared plus negative 2 squared. Basically just the Pythagorean theorem and or the distance formula. So that's going to be the square root of 20. And I'm not sure I'm really worried about it, but you can rewrite that as 2 times the square root of 5. So that's r. Nothing terribly exciting on that one. We still need to figure out theta. And for me, there's one really good choice. I mean, you've got 6 trigonometric functions you can use to work here. We're probably going to stick to sine, cosine, and tangent. Those are the easiest ones, the ones we're most familiar with. Nothing wrong with that. But which one looks easiest to work with amongst those? I mean, if you did, say, the cosine, you'd have 4 over this. Yeah, not looking so good. Yeah, tangent looks pretty easy to work with because you've got a side of 4 and a side of negative 2. So the tangent of theta is going to be opposite over adjacent, so negative 2 over 4. Theta is the inverse tangent of negative 1/2. When you go to your calculator to find this, make sure your calculator is in radian mode. You're not going to get a nice answer in terms of multiples of pi. That's okay. Inverse tangent of negative 0.5 should give me a negative angle, so negative 0.46, etc. If you wanted to figure out, well, gee, what's that look like? You can multiply by 180 and divide by pi. That converts it to degrees, so about a negative 26. 0.56 degree angle. Approximately. Overall, r and theta was 2 square roots of 5 and negative 0.4636. Now this one didn't work out nice and even. That's okay. You don't have to. The one I'm going to give you next does work out a little bit friendlier. Before I give that one to you, are we okay with 14? How well do you remember polar coordinates? Is this like, oh yeah, I got this, or was like, oh man, I haven't seen this in a while, or somewhere in between? What's that? Year and a half ago? Been a while for most of you guys, or yeah? All right, so the refresher doesn't hurt? No? Okay. Here's one for you. Problem number 16. 3 and negative the square root of 3. So again, this is an angle in the 4th quadrant, although I guarantee that this one's going to work out a little bit nicer than the previous one. So I want r and theta instead of x and y. So there's theta. And I'll also need to figure out the radius. Bless you. Okay, so let's start by finding r. R is going to be the square root of 3 squared plus negative root 3 squared, which gives you the square root of 9 plus 3, or the square root of 12. And it might be helpful to write that as square root of 4 times square root of 3, or better yet, 2 square roots of 3. So 2 square roots of 3 here, minus square root of 3 here, and 3 on this side. If you're figuring out theta, you've got a couple good choices, but one nice one is the sine of theta. Because if you calculate the sine of theta and you've taken the time to simplify your radius like this, you get that the sine of theta equals negative root 3 over 2 square roots of 3. And what magical thing happens? Yeah, you get negative 1/2. And you might remember this angle, you might not. That's okay. Calculus is done in radians, that's true. But a lot of you might not recognize the answer if you kept your calculator in radians. So what I would suggest is that even though our answer is going to be in radians, we just take a kind of a sneak peek here and look at it in degrees. So the inverse sine of negative 1/2 or negative 0.5. Oh, negative 30 degrees. Oh, yeah, I remember that one. That's negative pi over 6. So, negative pi over 6. Or better yet, if I'm asking for an answer for theta between 0 and 2 pi, for instance, then that answer would be 11 pi over 6. Be an equivalent answer there. So probably what I would be expecting on an exam would be 2 square roots of 3 and 11 pi over 6, like that. Are we okay with problem number 16 there? Let's take a look at some other ones. Problem number 26. We're going to convert from an equation in rectangular coordinates to an equation in polar coordinates. So x squared plus y squared minus 2ax equals 0. Now, I'm pretty sure that if you spent some time completing the square, what you would find is that this is a circle with a center at A and 0 on the x-axis and a radius of A. I'm going to kind of skip through that a little bit and just go to converting this to an equation in rectangular coordinates. Let's remind ourselves of a couple things here that are helpful. X squared plus y squared. Does anyone remember what that was equal to? R squared. And x was equal to r cosine of theta. Y is equal to r sine theta, but I don't think we need that one here. This part right here, that's your r squared. So that's easy. Wait a minute, wait. Give me some love.
That was easy.
Yeah. So that's an r squared minus 2a times r cosine of theta equals 0. Typically in these problems, you like to have r by itself. So let me move this term to the right-hand side and get r squared equals 2ar cosine of theta. I still don't have r by itself, but my last step here is I can divide both sides by r and get r equals 2a cosine of theta. That's it. Wanted to get an equation that had r by itself. So r depends on theta. And that's how you can graph this thing. Okay. Are we all right with problem 16 here? Kind of a little sleight of hand there, but it worked out pretty nice. A is just a constant. So tell you what here. It's about time maybe we looked at some of these things, take a look at their graphs. So let me quickly go over to Desmos. And let's type in R equals 2A cosine of theta. So you'll find theta underneath the ABCs, like that. And I'll do a slider for A. So what do we see here? Exactly what I predicted. A circle with center at A, in this case A is 1, on the x-axis. Now if I change A, what happens? Well, changing the size of the circle. So let's pick 2. Now 2 is the center of our circle, and that center is right on the positive x-axis. If I had made this a sine of theta, then this is going to be on the y-axis. So let's do sine of theta, and there you go. Same kind of thing. You can make it bigger or smaller, or hey, let's go negative. Whoa. So you can do lots of things with this. All right, good question. Thank you. When we get to graphing these things on a graphing calculator, then I'll talk a little bit more about how we generate those graphs. For now, let me look at problem number 24. X squared minus y squared equals 9. Does anyone remember what this graph is going to look like? Not a half circle, but I appreciate the guess. Let's get rid of these. It'd be a circle if I had a plus there, but I don't. I have a minus, so you get a hyperbola. So you get two branches of a hyperbola. They face away from each other. They open around the x-axis. So let's see if we can't get an equivalent equation in polar coordinates. Now, polar coordinates are good for some things, not really good for other things. For instance, one thing that polar coordinates is good for is the equation of a circle. Now, in rectangular coordinates, here's a circle. It's not a bad equation. It's just, But how about if I try and do that in polar coordinates? In polar coordinates, let's take a quick look at that over here. It'd be x squared plus y squared equals 9. So that's r squared equals 3 squared, or r equals plus or minus 3. So, wow. That's a lot simpler form of an equation. If I write r equals 3, there's my graph. So polar coordinates can make some equations very, very simple. It's nice to work with them. One of the things that I like with polar coordinates is that it gives me a chance to be romantic. Woohoo! You can make a cardioid. So cosine of theta. There you go. So let's get rid of this. Actually, maybe just do sine of theta. Sine of theta. No. Let's try one more thing. There we go. How about that? Woohoo! Romantic, right? Isn't that great? All the chicks in college and grad school are like, woohoo! Not really. What's that?
On a card, this has 1 minus sine theta.
Yeah, that'd be great. A great math nerd greeting card, on Valentine's Day. I'm not sure my wife would really be bowled over by that, but who knows? Anyways, some pretty nifty shapes here that you can get with these cardioids. Now, this is a very simple equation in rectangular coordinates. I mean, in polar coordinates. Boy, it'd be nasty if we had to solve for y and plot it in rectangular coordinates. So some things work out great in polar coordinates, some things don't. So it's nice to have both. Let me continue with problem number 24, though. Kind of got a little sidetracked. Remember that we have x is r cosine theta and y is r sine theta. I'm also going to remind you of an identity that I kind of think we're going to be needing. Cosine squared of theta minus sine squared of theta is cosine of 2 theta. Okay, so let's substitute in here r cosine of theta squared minus r sine theta squared equals 9. let me distribute that square. So it's r squared cosine squared of theta minus r squared sine squared of theta equals 9. And I can factor out the r squared. This whole term then can be replaced by cosine of 2 theta. I'll try and give you a heads up if I think you need to know that identity, because I know that, if you don't use it, you lose it. You're probably going to forget it. So if I anticipate you needing that, I'll let you know. What are we going to do to solve for r? Anybody? All right, divide by cosine of 2 theta. Let me just do a sound check here to make sure we've still got sound. Yes. Okay. R squared equals 9 divided by cosine of 2 theta. Then what? What does r equal? Yeah, square root of this whole thing. Let me just put 3 in the numerator and plus or minus square root of this cosine of 2 theta in the denominator. So there you go. I don't know. Personally, I think I like this better in rectangular coordinates. But like I said, some work better in one form than the others. Should we try and graph that, or do you have confidence in your instructor? Confidence. I was waiting for somebody to give me the right answer. I was thinking of all kinds of great problems to give you guys on the next exam, but somebody came through with the right answer. That's good. All right. Let's try a different one. Problem number 38. Theta equals 5 pi over 6. Now this one's kind of a little bit different. It's strange. So let's take a quick look at its graph. So I'll do this for myself. Problem 38. Let's steal a theta from up here. And theta equals 5 pi over 6. You know what? It doesn't like that. Bummer. Why don't you like that? Sorry, can't do that yet. Bummer. All right, guess we're going to have to do that without it. So let's go back over to the equation then and see if we can't figure out what this looks like in rectangular coordinates and then kind of make sense out of it from there. I gave you one expression at the start of this for theta. Does anyone remember what that one expression was? Theta was equal to tangent inverse of y over x. Okay. Well, if I want to solve here, what I can do is take the tangent on both sides. So that it is the tangent of the tangent inverse of y over x equals the tangent of 5 pi over 6. Do I get any simplification here? Yeah, the tan and tan inverse cancel. All right, so that's going to give me y over x. And just trying to think here, tangent of 5 pi over 6 is negative 1 over root 3. So if I solve for y, I get y equals negative x over the square root of 3. So you're going to get a line straight through the origin at that angle, 5 pi over 6. Yay. All right. So there's a couple examples of going from rectangular coordinates to polar coordinates. and of course the other way around as well. Trying to think if I want to do one more. Let's do maybe one or two more. Let's go the other direction. Let's start out with problem number 28. X equals 12. Doesn't get much simpler than that. But if you needed to, you could convert this to an equation in rectangular or in polar coordinates. How would you start out? Dawood, any ideas? What would you start out with? Yeah, x equals r cosine theta, so this is r cosine of theta equals 12. So r is 12 over cosine of theta. Personally, I think I like this one better. This looks a lot simpler than this one. But that's nothing that contradicts what I've said all along, that sometimes one is better than the other. And finally, let's get around to problem number 34, and then talking about these graphs. So problem number 34, r equals negative 5. Well, I'm going to cheat a little bit, and let's square both sides and get r squared is 25. So we get x squared plus y squared equals 25. What's that equation look like? Circle. Where's the center? Good, 0, 0. And what's the radius? Wait a minute. It went silent on me. What's the radius? 5. Thank you. Radius is 5. Let's start to graph these things. So take out your graphing calculator, and let's learn ourselves a different mode. So hit the mode key and go all the way down to function, and then cursor over to polar and type in polar. So this should be the same regardless if you got an 83 or an 84 or an 84 color. It should work out the same either way. When you've made that selection, hit the y equals key. Tell me what you notice that looks different. Yeah, you've got r instead of y. So r is some function of theta as opposed to y as a function of x. Okay. Let's type in a couple things. Let's type in a 5 here for the first equation and a negative 5 for the second equation. Now, a little trick here. If you cursor to the left of the y equals or the r equals in this case and press enter, one of the things you can do is, actually, you know what? Not even that. My bad. If you just put the cursor on the equal sign and press enter, it'll turn that graph off. I don't want to graph that second equation just yet. I'll come back to it in a minute. Let's set up our graphing calculator to give us a good graph of this. If you hit your window key, you should see something that looks like this. And now what happens when you're graphing things is your calculator is going to start out with this value of theta, put it into your expression, calculate the radius, and then jump up by a little increment called theta step, and then repeat that process. It's going to plot another point, and it's going to eventually connect all the dots. Now, does anyone recognize 6.28318, etc.? 2 pi. So set your calculator from 0 to 2 pi. Now when you press enter, the pi symbol is going to disappear. That's okay. This theta step, we don't want it too big. We don't want it too small. We want it to be the baby bear of theta steps, right? Just right. Not too big, not too small, etc. You guys aren't catching my Little Red Riding Hood reference. All right, that's fine. When you watch it on tape, it'll be really funny. Okay. As far as the X min and X max are concerned, you know, it's tough to look at these things and know. So here's a little shortcut for you. Instead of trying to deal with all that ourselves, hit the zoom key and then zoom 0. So zoom 0 is zoom fit. It will adjust your window to perfectly fit your graph. So you should get something like this. Now, does that look like a circle? Not exactly. Looks like a circle that kind of got squashed, right? A very height challenged circle. So to make this actually look like a circle, we're going to hit the zoom key one more time and hit zoom 5, zoom square. And that'll square it up. And now your graph looks like it should. It looks like a circle. So those two keys back to back, zoom fit and then zoom square, give you a good look at what your graph should be. Now, let me play around with our window a little bit and teach you a little bit about how these graphs are working. I had theta step was 0.015. What if I did something like theta step is about 0.25? What do you think is going to happen now? Yeah, all right. It worked a little bit faster. Let me do theta step as 0.5. That's a little bit too big, but hopefully it'll get across my point. All right, there you go. So it plots the first point, and then it jumps up to theta is 0.5, and then theta is 1, and then 1.5, etc. And basically, I don't have enough values of theta to get the nice smooth graph that I expect, right? So, you know, you want to try and find a happy medium. 0.1, I guess, probably would have worked out pretty good. Or maybe I'll do 0.05. I'll leave it there. One other thing. Watch the direction that my graph is traced out. It's traced out counterclockwise, right? Let's go down now and graph this one. So hit the y equals key, shut off this graph, and turn on the second graph, and see what happens. Do I get the same thing? I get the same graph, but there is a difference. Did you catch it? What's the difference in these two? Donnie? Yeah, it started out here, all right? And, you know, the way it proceeded was a little bit different. So let's take a closer look at that. Let me just do this again. I'll make this a little bit smaller, kind of slow it down. But it starts out at the negative x-axis. It's still going counterclockwise, but it just started out here as opposed to here. So that's the difference in that one. You're still going to get the same thing either way. Circle centered at 0, 0, radius of 5. Okay. Let's work on our handout a little bit. Let's take out this one. And you can kind of play along with this a little bit if you'd like. You can do it on your graphing calculator. In fact, let's do one. Let's clear this out, both of these, and let's take a look at the graph of r equals sine of 2 theta. Notice that when you press the x key on your calculator that you're not getting an x, you're going to get a theta. We're going to keep our window the same in terms of 0 to 2 pi. But there's a little sequence that you should follow when you're graphing these. Start out with zoom fit, so zoom 0, and then zoom 5. And then we'll see if we can't match our graph here. So zoom fit, and then zoom 0. You know, one thing that annoys me about the TIAs is that they're pretty slow. The Inspires actually have a pretty good processor. They're pretty fast. So this looks kind of like this one here. It'll look a lot more like it if you follow this up with a zoom 5. All right, nice. So pretty cool. Cloverleaf, right? Cool. Who would have thought that you'd be doing cloverleafs in your math class? Nice. Now, if I replaced that function with cosine, then I get a similar graph. I get this one over here. So the only difference is that one has been kind of tilted or rotated from the other one. This one, if you take the time to look at it and see how it's graphed, it's going to start out on the positive x-axis and then come through here. Sine starts out here and then traces up like that. Take a minute and see if you can't figure out the pattern. Because we go from sine of 2 theta has 4 leaves, but then sine of 3 theta only has 2 leaves. And then, okay, so what's going on in the back? Sine of 4 theta has 8 leaves, but sine of 5 theta only has 5 leaves. So what's going on? And you can see the same thing happens for cosine. Cosine of 2 theta, cosine of 3 theta. Yeah. Even, the number of petals is doubled. Odd, the number of petals is the same. So I got a little chart down here that you can kind of fill in a little bit. If we have n is 3, then you should have 3 leaves. N is 4, 8 leaves. Now when you're drawing these things, let's take a look at the cosine. So I'm just going to replace the sine of theta here with the cosine. Just type right over it, cosine of 2 theta. And then I should be able to hit the graph key. Notice where this one started out. It started out on the positive x-axis and then moved up here. The reason I point that out is because the positive x-axis is really the axis of symmetry for one of these leaves. And when we start trying to find the area of these things, what we can do is try and find the area of half of that leaf and then multiply it by 1, 2, 3, 4, 5, 6, 7, 8. Multiply it by 8. But what you're going to need to know is the axis of symmetry for these things. Now that's also true when you start working with sine of 2 theta. Sine of 2 theta is going to have an axis of symmetry right here. Oops. So the question for us is going to be to figure out, all right, well, when do we get to that point? Or when do we get to this point? Because your sine graph is going to start out here, increase to a maximum, and then come back down. And the shortcut answer to this is this. When we have sine of n theta, it's going to reach its maximum when you get the sine of something that gives you 1. Or in other words, n theta equals the sine inverse of 1. What's the inverse sine of 1? What angle has a sine of 1? Yeah, pi halves. Thank you. 90 degrees. So if we divide by n, theta is going to be pi over 2n. That's going to be where you're going to get that axis of symmetry for these functions. And that's what I have down for you here on the back of your sheet. So that would be 3, 8. So see if you can't fill in these couple here. Let's see. Is that right? Let me see here. It says pi over n or pi over 2n. This is going to be if you have an even number or an odd number. Does that work? Let's see. Well, we'll find out. We'll find out. Let's do it this way. Let's go back to the sine. And you can kind of help yourself if you would. We've got our graph. And what we can do is we can trace it. We can try and figure out, well, where does that point occur? Is it where I think it is? Let's find out. So almost done, almost done. All right, so you hit the trace key. Trace at an angle of pi over 4, so second pi divided by 4. This opens up once you hit a number. And it's right out here at our maximum. So pi over 4 is correct. Let's see what happens at sine of 3 theta. And let me also take the opportunity to show you something interesting. Why does this only have 5 leaves instead of 10? Why is it only have 3 leaves here instead of 6? I'm going to put a little marker or a tracer on my graph so we can follow it along. Let's see, this one right there. Okay. So this is just going to give me a little more insight into what's happening with our graph. So I'm tracing it from 0 to 2 pi. And we see our leaves here. Don't quite see all the bottom of that one. That's fine. But watch what happens here. The reason you're not getting 6 leaves is because the graph is tracing over itself. So that's why you're getting 6 leaves. Or 3 leaves. You're getting the same 3 leaves twice is essentially what's happening. Alright, so trace. Let's do pi over 3. No, we just do pi over 6. So pi over 6. Let's see. Pi, second here, pi divided by 6. Pi over 6 should be this point here. Yes, it is. Alright, so as far as the back of your handout is concerned, I'm not sure where this came from. I'll have to talk to the author about that. Me. There we go. Never happened. Beautiful. So pi over 2n. So this is going to be pi over 6, pi over 8, and pi over 10. Now, like I said, it's helpful and it's necessary to know where that axis of symmetry is. The other thing that's useful to know is how far you have to go to get this graph plotted once. Now, it's basically going to be one of two things. It's going to be 0 to 2 pi. If you're talking about an even value of theta, it's going to be 0 to pi. If you're talking about an odd value in front of theta. So 0 to pi, etc. And let me go back here and adjust my window. If I go from 0 to pi, I should still see the complete graph with 3 clovers. Let's see. While that's going, we can finish this off. 0 to 2 pi and 0 to 2 pi. Perfect. And it went around exactly once. I still have the graph. So I don't need to go all the way up to 2 pi in order to get a complete graph. Okay. Are you catching on to these ideas here? The same thing here is going to apply here. The nice thing about the graph of the cosine is that the axis of symmetry for that first petal is always 0. So that's a nice thing about that. So what should you be getting from this handout? You should be getting how many petals there are and where the axis of symmetry for that first petal is, because that's how we're going to integrate and figure out these areas. So we good on that part? All right, no descent. Here's one for you to play with. Problem number 50. Let's just write it here. Problem 50. R equals 3 times the sine of 5 theta over 2. Now I played around with different intervals to try and figure out an interval of theta that graphed my previous function. What if I wanted to graph this one and get the complete graph? What do you think I need to do for theta? Put it in your calculator. So we want 3 sine. I'm going to be lazy. Instead of writing 5 theta over 2, I'm going to write 2.5 theta. Same thing, right? Your calculator doesn't care. It doesn't have feelings. You don't have to be nice to it. All right. I can go play hockey, leave my calculator in the car, and won't complain when I come home. I don't have to bring my calculator flowers. It's nice. All right. Sorry. What's that? No. Sorry. Let's see. So 0. Let's do 0 to 2 pi. That's a good place to start. And as far as the x and y coordinates are concerned, let me suggest negative 4.5 to 4.5, and on the y-axis negative 3 to 3. That's going to be what's called a square-looking frame. The width is 1.5 times the height, which is roughly the dimensions of our screen. So if you hit the graph key, let's just see how it goes. See if it looks like you get a complete graph. Personally, I think I need to make my theta step a little bit bigger because this is taking too long. All right, so interesting. Do you think that's it? Let me make a couple adjustments. Let me make this a 0.05. Get that to graph a little bit farther. But what if I go to, say, 3 pi? And then graph it. Well, that was a good call to adjust theta step, because this is graphing a lot faster. Does it look like I got a complete graph here? Well, what should I try next? 4 pi? All right, so let's try 4 pi. And now graph it. Does that look pretty good? Hopefully. Let's try 5 pi. 5 pi. And if you have that tracer on your graph, it helps out because you can see if it starts to trace over itself. So we did 4 pi, and 4 pi looked pretty good. We got a complete looking graph. And then at 5 pi, look, the graph is starting to trace itself again. So 4 pi was enough for this particular function. So the interval you want here is 0 to 4 pi. Yay. Okay. Want to take a break here? When we come back, we'll finish up. We got to do the derivatives of functions in polar, but it's not a bad place for a break.